Okay, welcome back from break, everybody. So we're going to dive right in now to sort of the second half of the program before the breakout sessions, and that is our access panel. So we have 4 awesome panelists lined up today to talk to you a bit, and so I will introduce them as we go. And first up, we have Issa Nesnas from JPL, who is going to talk to us about a variety of things, kind of focusing on robotic system design and how you might go about thinking about that. So Issa, are you back on with us? We're not back from break yet. Okay, we'll give Issa one more chance. And if not, we'll just jump in with somebody else and come back. All right, well, that's fine. I'm not sure the order is so important here, just the topics are all a little related. So we'll come back to Issa second then, and I will.
Hello?
Oh, are you here?
Yes, I'm here. Sorry.
Oh, sorry. Okay, perfect. I know jumping in right after a break first is tough.
Yeah. No, I was just writing an email and I heard my earpiece is speaking. So.
All right. Well, perfect. So, are you sharing your slides, Issa, or are we sharing them for you?
Yeah, I'm actually sharing. Let me go ahead. Can you see my slides?
Yes. Yes, there it is.
Perfect.
And they look great.
Okay.
Thanks.
Shall I go ahead?
Yeah, go ahead.
Okay. Good morning or good afternoon, depending on the time zone you're in. My name is Issa Nesnas. I'm a principal technologist, robotics technologist at JPL. And what I'm going to talk about is designing for the extremes, looking at robotic system design. So my presentation breaks into 3 parts. The first one is understanding the extremes, understanding the environment, and then looking at system design. And what do I mean by understanding the extremes? When we talk about extremes, we have to think about what extremes are we talking about, especially for extreme access. Are we talking about the terrain? And is it the terrain topography, but also the regolith, which we heard about earlier this morning, regarding our knowledge of it, and then its challenging nature. But also another form of extreme is the distances we need to cover or the areas that we need to cover. And when we talk about extreme access, another form of extreme is getting through these layers of regolith and cryogenic material if we need to go deeper, so going through that material in depth. So I'll focus on the first 2 for my talk. The second part is understanding the environment. Now, we talked a lot about Shackleton Crater. This is a picture of understanding the hydrogen abundance by weight on the lunar South Pole. So here's Shackleton Crater. And we can see some of the signatures and the abundances in other regions compared to Shackleton. But when we look at how does this overlay to PSRs, then you can see these PSRs here in these different regions. And one thing you want to look at, where are the concentrations of the resource that we're looking after and the relations of the PSR, as we heard from Austin's talk earlier this morning. But a third part to this is, what does the terrain look like? Because we need to eventually access this. And if you look at, this is a map of the slopes, and the red here is slopes that are greater than 35 degrees, and the purple is 0. And you want to stay in the purple and the blue regions if you want to make access easier. So there are regions where they're permanently shadowed, and they have the resources, and they may be maybe easier to access than Shackleton Crater. Now, there may be other reasons to target the Shackleton Crater rim for the permanency of the light in the certain parts of that region. But it'd be good to take a holistic look at the different parts of the lunar South Pole, because those challenges are all very coupled. So let me just go through this again. This is the PSRs, and this is the hydrogen abundance map. Now, of course, these things will evolve as our understanding of this and further mapping and further missions will inform this. So I think this will be something that will evolve over time. Okay. The other thing is to understand what information we have and at what resolution, which is important for surface access. So if we look at our spatial coverage and our 3D information, topographic information, this table summarizes the information we have from the narrow angle camera on LRO in terms of resolution. So it's important to remember that in permanently shadowed region, the information we have tends to be much lower resolution. So in some cases, we do have things on the order of 200 meters per pixel from the diviner maps, but also we have in the PSRs, we have 1 by 40 meter pixels based on some long exposures that were taken with a narrow angle camera. Now, as we have additional missions orbiting and acquiring additional imaging of these PSR regions, we'll get much better understanding of the topography in these dark areas. So some of the upcoming missions that will inform our understanding of these regions are here. But it's important to note in terms of the 3D reconstruction, where we are able to reconstruct 3D topography from the narrow angle cameras, we only have very limited coverage on the order of 2 to 5 meters per pixel at that resolution, but we do have full coverage at the much coarser resolution than the Kaguya camera. So when we think about terrain access and mobility in PSRs, one thing to keep in mind, as we know from multiple the Apollo and the Surveyor missions, we have not seen a lot of variation in terms of surface properties and processes between the different sites that we visited. And so the expectation is that similar things will be in the polar regions because the processes that form the surface of the moon are the same everywhere. However, it's important to also keep in mind some of the differences that may be in the PSRs. One of the things that does impact mobility is the grain size. And because there is no thermal cycling, there's no thermal cracking, the grain sizes may be different in the South Pole regions. We heard about the electrostatics and keeping that in mind as we consider mobility system. The other thing to note is the absence of large-scale pyrodeposits because there's no volcanism near the poles. And that will affect the properties of the regolith, which may differ from the equatorial regions that have been visited. So the things we don't know today about the lunar South Pole is the morphology at the 1 to 10 meter scale, which is a relevant size for mobility, but also we don't know the compaction due to the lack of thermal cycling. Okay, here we go. But the other thing is to really appreciate is actually mobility in uncompacted, unconsolidated regolith could be actually quite challenging. I share with you here a plot of performance of slip measurements on different slope angles. And these were studies that were done for the Mars rovers. And they were done in a way to simulate the slope angle. So these are supposedly more accurate representations of the slip versus slope measurements. And this is done in, unconsolidated fine sand. And you can see that as you get up above 15 degrees, you could start experiencing very high slip on the order of 70, 80%, 90%. So traversability. So if we want to look at wheeled mobility and traversability, trying to stay below the 15 degrees, you're still experiencing somewhere between 50 to 70% slip at these angles when the terrain is not a bedrock, it's finer regolith or softer regolith. And as we get into these crater walls, where some of the material may not be as compacted on the interior of crater walls, slip could be fairly high. Okay. So that's on understanding the environment and the challenges associated with mobility related to that environment. Now, when we think of access, before we even start designing the mobility, the first thing we want to do is understand the payloads and the operations that we need to do. What is it we're bringing to these sites in terms of equipment, in terms of excavation, in terms of scouting, and what are the drivers for the operations of the payload we're bringing there? And then understanding the regions and distances that we need to cover and the areas that we need to cover. And then also what duration do we need to cover those distances by? And also understanding the nature of the investigation we need to do at these sites. So there are other very highly coupled things that actually do drive and affect the mobility design significantly, which was touched upon early this morning, which is how we're going to get energy and power, especially when you get into more extreme areas, highly sloped areas, where occlusion starts impacting your access, your line of sight access. And that not only impacts power, but also impacts communication. And we heard earlier on, thermal management is key. Operating at these cryogenic temperatures is a major challenge that drives the design of the whole system. And of course, the mobility challenges. And then also how we're going to deploy these payloads or these equipment and do the operations. Now, if we're thinking of scouting the regions to understand the concentrations, then there are, what is the big picture architecture? Are we going after a surface axis, meaning some type of vehicle that goes on the surface, or are we going after an above surface axis where we're using landers and hoppers to get into these? Some of these crater wall traversals are not easy, and I think it'll be good to look at the trade space to access the regions that will be accessed. Now that may be easier for scouting, and when we start talking about hauling a lot of material, that also plays into the architecture in terms of access. Now, in the area of surface mobility, just other things to consider: the distances, the speeds, and again, the slopes. Even these very, what may seem shallow slopes actually play a significant role when the regolith is not compacted. And then rock distributions and ground clearances. And another factor that plays into it is the cost of transport. How much energy are we expending to carry a certain mass by a certain distance? And then the other consideration is the stability on the slopes, depending on the operations we're going to do, whether it's deep drilling or whether it's some kind of excavation. And then the other thing is the redundancy and the resiliency, because we don't want these things breaking in these situations. And complexity is a big driver that we want to try to manage throughout the process. And the other part, which Terry will touch upon a lot more, is the navigation, the sensing, and the autonomy needs and the operational complexities that go with it.
So Issa, another minute or so?
Yeah, actually, I'm going to stop here. I do have 2 slides that gets into the detail of surface mobility designs, and and it's very much focused on wheel vehicles. So basically, what would drive your type of mobility? Are you using skid vehicles? Are you using steered vehicles? Are you using omnidirectional vehicles? Are you using active suspension or passive suspension? And if you look at the developments of different prototypes, they kind of cover, these are examples of what has been done in these classes of systems. And maybe I will end by key thing when thinking of surface mobility is the energetics, because you want, what are the key drivers and how do they influence your mobility design. A lot of times when we design systems that are not human operated, we have to look at the worst case scenario and design based on that. That does not lead you to the most energy efficient system. So we have to think about, are these going to be human aided if they get stuck, or are they going to have to operate on their own without any human interference or interference from other assets if they do get stuck? And that's how some of these systems were designed for past missions. This is a very busy table. There's a study, and this has actually been published, regarding how do these different architectures of mobility system fare based on certain design criteria. I won't go through that, but let me pause here and turn it over. Are we going to take questions now or at the end?
I think there's a few questions in the Q&A. If you get a chance, you can kind of chat, answer them there, and then we'll take bigger questions at the end.
Okay, good. Thank you.
Perfect. Thanks. That was really interesting. Okay, so we're going to continue now with, let me see if I can do this. Dimi Apostolopoulos. Pretty close.
Beautiful, Angela. Awesome.
Thank you. My Greek is a little rusty, but he's going to continue talking about some of these access and mobility challenges to build off of what Issa just presented.
Awesome. I hope you can see the presentation. If you give me 1 second here, I will do the quick. You should be able to see. I hope you see the right screen, or?
Yes, that looks great.
Okay, awesome. Okay, so my name is Dimi Apostolopoulos. I'm founder and CEO of ProtoInnovations, LLC, in Pittsburgh, Pennsylvania. And I will be offering a few remarks. It's a very short presentation on mobility controls and manipulation, and the synergy of the three in relation to surface systems. Issa's presentation was great because it provided a lot of the background and references in relation to the environment and the specifics of the environment that apply to what I will be presenting, obviously. So my presentation is kind of dovetailing nice into what he showed. Okay, so the focus is site access for regolith excavation and transport. This is this portion of the presentation. What I've tried to do with this presentation is to summarize a number of experiences and insights from many years of space relevant system design and robotics. So my remarks will be very selective. They will cover only a small portion, obviously, to what someone could present in this time frame. And I think they apply equally to robotic and human assisting systems, as you will see in the next few slides. I've tried to keep things at a level that would be understood by everybody. And I want to emphasize, and what I will be showing is, I believe they have broad value and they're scale independent. The word scaling, the word systems, we heard them earlier from Alex and the other people who made the introductions. The understanding of systems is extremely important, and also the relationships between systems of systems and also within its system, what may be critical elements for this future architectures to be implemented. Hopefully this will also help with the conversation, and the slides will include a mix of, as I said, experiences and also ideas on needs in terms of technology and also R&D directions. Okay. Oh, second, here we are. Okay, so on the left side, there was a lot of discussion about the environment, and each single line on this slide represents many years of development, probably billion-dollar programs in order to get to sustained presence on the moon and achieve the vision of something like our LS2 that Alex presented earlier. The other component to system design and looking at certain components of it is the fact that it has not only to meet the requirements of the lunar environment, but also to address the operational requirements related to ISRU, which are pretty hefty in terms of forceful engagement, the types of processes that may be happening on board, the systems that will carry them out, the transport of material, and also interconnects to other systems. This is going to be an enormous endeavor, and so those interconnects are going to be critical. What I would like to focus in the next few minutes is to discuss the certain elements in terms of mobility. Issa started that conversation, controls and manipulation. I believe those three elements are critical for any system or any system of systems that will be implemented on the moon. And what I will try to attempt to do in the next few minutes is to make really the connection, to present each one, and also make connections of what is really the intersection of the three and the significance to these future architectures. Starting with mobility, there are certain things that we have learned over years of robotic system development, robotic space system development, and I'm sharing those in this slide. The first one is that fundamentally, one must design something that will have high intrinsic terrainability. This is very fundamental in the sense that you want to have a system that mechanically can perform very well, as opposed to have something that has some mobility and then expect the controls to do much of the work on top for robotic systems. And how can someone design a system that has high intrinsic terrainability? We do know of a few very critical metrics. For example, the drawbar pull at the angle of repose is very, very key. It's these are kind of ubiquitous metrics that someone can use to design really high performance, high intrinsic performance mobility systems. The second is to give ample space for stability, both static and quasi-static. A lot of space surface systems are fairly slow, so it's more a quasi-static type performance, but it's low gravity. The performance is slightly different, so that's an important consideration. The last thing is obstacle negotiation, and there is specific ideas and specific metrics in relation to those. If somebody were to design systems that really address those three very, very well, fundamentally, you have done some good work in terms of developing something that has really good intrinsic terrainability. The second thing is effective actuation. By effective actuation, I mean that the systems, one must identify the points of interaction between any system on the surface of the moon and the environment, which are used to create traction, okay? In order to move, in order to provide that resistive force, in order to drill, etc., whatever it may be. It is essential that those, based on our experience, that those points are powered, meaning wheels that operate and are critical to move over, they have to be powered. Unpowered wheels or unpowered degrees of freedom are very, very hard to, they don't contribute much, and they're very hard to really provide for what the purpose of a specific mission or operation or a task. The second is to treat those different degrees of freedom as independent. And that's very fundamental as well, meaning to be able to power them, to be able to actuate them, and be able to control them. This comes very, very handy in the things that we'll discuss in the next few slides. We have also learned that kinematic simplicity is extremely important for any designs, more so for lunar rover design. The first one, and some of the kind of important considerations in relation to kinematic simplicity have to do with modularizing, for instance, the locomotion subsystems, try to keep them as clean and their interfaces as discrete as possible. Another very important consideration, we saw, for example, the big crane that Alex showed earlier in the first presentation, is that you expect to have systems that may need to move, they may need to articulate. Minimizing the number of articulations is critical for the moon. It's critical, obviously, for environmental reasons, but also in terms of controllability and ability to properly manipulate the environment. The next thing is integrated sensing. In the simple diagram I showed in the previous slide with mobility, controls, and manipulation, what one could add more circles, including sensing, including autonomy, etc. I'm just trying to give a snapshot, an introductory snapshot for people to just get an idea on the significance of those elements. But specifically for mobility, sensing is extremely important because fundamentally it's used to as a measure to provide feedback and then allow for controls to be effective and also for manipulation then the tasks that the system can do to be done properly. Motion and force are the key areas and focal points of sensing. And generally speaking, what we have been studying in the last few years in the robotics community and thinking on how to improperly implement is this notion of this class of distributed proprioceptive sensors, like which exploit, for example, the current that goes into a motor, or some force sensor at a very appropriate point within the locomotion system that provide information in a very local sense at the source that is needed to be sensed properly in order to help with controls. Environmental and task robustness, it's a huge topic of its own. Issa touched on this. It's really beyond the scope of what I can cover in 10 minutes, but it's extremely important. Okay, then going to controls. This will play. I thought it was going to play. I'm sorry, I thought that the movie was going to play here, but it's not happening. Right. So in terms of controls, a couple of very important things here. The first one is that in order to achieve high mobility on the lunar surface, there are three important considerations which have their own difficulties and their own special requirements, if you wish, in relation to a mobility system design, a control system design. The first thing is that any system that has mobility has to be able to perform in a manner that it's safe in response to the environment, meaning that a system cannot sleep excessively. Issa showed one example. It cannot embed itself. It cannot topple itself, let's just say, on a crater. So the ability of a control system to detect conditions that may lead to compromise of safety and address them is essential. The second thing is efficient use of resources. This is more of a technical subject, but it relates to the ability of a rover to utilize its own power, its own resources, its own energy that's available as efficiently as possible. This is important for example, in executing certain types of missions where there may be limitations in terms of power or in limitations in terms of energy. How does a rover control itself or its mobility while taking into account how much available power it has in order to do, or energy it has in order to do its intended mission? The next thing is, yes.
Just a couple more minutes.
Okay, thank you. The last thing here is effective use of intrinsic trainability, which is if you have a mechanism that's very effective from its mobility standpoint, then when you add the controls, it should help basically, it should complement that intrinsic capability. And how this is done is quite important. For the manipulation portion of the controls, because we're talking about systems that have mobility and manipulation, the key thing in terms of controls is to manage properly the forceful interaction with the environment while the system is able to move. This presents a very interesting problem, and I will discuss this a little bit in a minute, the next slide. A couple of things in terms of new directions. One is that we're looking, and what may be needed for the moon is to have very dynamic and reconfigurable control architectures, because a rover may be driving on flat ground and then has to negotiate the slopes of a crater, and then we have to do drilling. As you imagine, the requirements in terms of mobility and manipulation may change for a given system. So the ability to reconfigure, dynamically reconfigure based on some policy, or based on some other technique. We have tested machine learning algorithms that learn the reaction of a rover that's experiencing in real time in order to decide the control strategy are very, very important references and considerations. Lastly, in terms of manipulation, I would like to offer you a little bit more of a different perspective in the last minute of this. Obviously, we're talking about forceful interaction and that forceful interaction has to take into account the rover, the tool that is employing, and also the environment. All three play a key role. We heard some from Erin, some from Issa on this. And what we are also looking into, which is, I think, a very unique and very interesting way to look into as we build manipulation systems for the moon, is that any degree of freedom a surface system has could be viewed as a manipulation unit, meaning if you're driving a wheel, let's say, and you have a rover and one wheel is driving, but all other wheels are staying at zero, that wheel is going to dig into the ground. It becomes an effective manipulation tool. Or if you steer a wheel and you keep it in a steering direction and you drive the rover or whatever the system may be, it could be used for trenching. What I'm trying to convey here is that for some of the ISRU tasks we're talking about or will be formulated for the future, anything on any of the systems you're describing could be used as a manipulation element, not just traditional manipulator where its degree of freedom can be used effectively in order to facilitate tools or to play the role of tools or to extend the dexterity that the system may have in terms of its ability to manipulate, to do very, very fine and different types of manipulations. What you see on the right side here, and probably I may have to close with this, is an example of one of the projects we have done in which we have partitioning this idea of manipulation units for each one of those, so to speak, to execute primitive actions. So for example, a trajectory, traction, or contact, we view those as primitive actions, some small, if you think, units of control. And if you put them all together, you can come up, or in different combinations, one can come up with different ways of managing and manipulating the environment in order to do more complex tasks and more diverse tasks, such as those expected for ISRU missions. Okay, and I hope I have one more minute. Unfortunately, the videos are not playing, or I'll try one more time, but very quickly, I think Erin covered the point of physical testing quite well. I will echo her comments about proper scaling and proper and good understanding of the different parameters that are to be used in a specific type of simulated testing, physical testing. What I also want to emphasize with this slide is that there has been quite a bit of magnificent work from universities and other centers on digital simulation work that can capture thermomechanics, different phenomena, mobility phenomena, and integration of controls on mobility systems that interact with granular media, etc., to a beautiful degree. And this is something for consideration. Hopefully we'll have this in the discussion later on to be considered as a means to really develop systems, develop architectures, develop systems with a lot more confidence as we gain more and more understanding based on the different lunar missions in the future. I will stop with this. Thank you for the invitation, and I'm sorry if I went over time.
Oh, that's okay. Thank you very much. That was really, really interesting, and hopefully gave people a lot of things to think about for the breakout sessions. So I appreciate that a lot. I don't know if there are questions in the Q&A thing that you could maybe address if there are. Otherwise, we'll get to some ones at the end. So, all right. So next up, we have Terry Fong from NASA Ames. And we'll be talking about autonomy considerations in these extreme environments. So your slides look great, Terry. But we can't hear you. Nope.
Yep. Terry, I'm afraid we're not getting sound from you. Can you check to make sure that you're not accidentally double muted?
How about now?
Oh, perfect.
Okay, let's try that again. Still good?
Looks great. Yeah.
Okay, good afternoon, everybody. Or for those of you on the West Coast, there's still a little bit of morning left, so good morning to you all. I'm the senior scientist for autonomous systems at NASA. I work for the Space Technology Mission Directorate, and I'm fortunately or unfortunately, depending on the time of day, also the deputy rover manager for NASA's Viper mission. What I'm going to talk to you over the next 10 minutes is some autonomy considerations for lunar future lunar missions. As was discussed earlier, if you're looking towards the future, especially more extensive, more I think capable long-term missions, a key question is really how do we make sure that these survive? How do they operate? How are they productive? It's very clear that that autonomy is an important factor in all of that, especially if you look at missions such as Alex presented at the very beginning, that have to operate for very long durations with high duty cycles and have to get a lot done. And where people, whether they're on the surface of the moon or on Earth, cannot be involved at all times. So to start with, I just wanted to briefly talk a little bit about autonomy from the standpoint of NASA and what we consider to be autonomy. Autonomy is a term that is often conflated with things like intelligence or smartness of systems or even AI. But the reality is that from a NASA point of view, autonomy is simply the ability of a system to achieve goals while operating independently of external controls. It's something that's been formalized since the 2015 NASA technology roadmaps. But what's important is to note not just the fact that these are things that are operating independent of external control, but the focus on the word system. We often think these days that we're going to implement autonomy simply by writing algorithms and software, and that's not at all true. The reality is that autonomy is a system level concept. That means that elements can include things like hardware, certainly software as well, but beyond that, facilities, personnel, that means humans at various places, processes and the procedures needed to do that. An example of autonomous capability is for the Curiosity rover on Mars. There's a capability called AutoNav that allows the system to autonomously drive from point to point while using its onboard cameras and computing to do everything from path planning to hazard detection and avoidance, and to robustly move the robot from point A to point B. Autonomy is something that certainly for missions, has a number of reasons why you would focus on trying to build those into those capabilities into the mission. It certainly could have to do with the cadence of decision making. Certainly for deep space mission, that's an important consideration because just of the communication latency to and from the spacecraft. It could also be when there are time critical decisions that have to be made on board, or maybe decisions are better made using rich onboard data, so more data than you could possibly downlink to Earth. But also, if you feel that making decisions in an independent manner improves the robustness or reduces the risk of the operations, maybe it improves performance, reduces costs. But there are other factors too. It could be used to reduce the variability that comes with training and proficiency. So even if you have astronauts on the surface of the moon working with the system, there are still differences between those different crew members. And finally, it may be the only way to achieve a mission objective requirement, especially if you think about large-scale, long-duration, continuous operation systems when you just don't have the time or the resources to have people involved at all aspects of that. Now, one of the things that NASA has done over the past several years is think about what are the key building blocks to enable systems to operate independent of external control. And here is a taxonomy that shows a wide number, a pretty broad range of different things that can feed into building autonomous capability. Certainly things in the area of situation and self-awareness, and that covers everything from sensing, perception, state estimation and monitoring, all the way through to things like anomaly detection are a key part of that. A system has to be able to be aware of the situation that it's operating in, has to be aware of itself, whether that's from a health point of view, a resource management point of view, anomaly or fault handling point of view. Secondly, there are lots of things under the category of reasoning and acting. And this encompasses everything that we've typically thought about in terms of planning, which could be at the mission level, the activity level, at a lower level like motion planning, through things like execution, control, fault diagnosis and prognosis, fault handling, and even adapting to those things. Another thing that's interesting too is the fact that these systems, even though they are operating independent, that doesn't mean that they are, completely disconnected from everything else. I mean, something can operate independently for a period of time and then need to interact with another system. That could be people, or it could be other hardware, it could be other systems. And so questions of collaboration and interaction are very important to support when you have a system that is supposed to be autonomous in terms of things like joint understanding of the environment or goal and task negotiation. And then, of course, there's everything you need to do to build and test these systems, everything from V&V to test and evaluation, operational assurance. The tools to support that might be modeling and simulation tools. And of course, underlying everything is a particular architecture or design that you're trying to use to pull this stuff together. So these are things that are important to think about as we're building not just systems for the moon, but autonomous systems in general. On the other hand, if we think specifically about the topic of this workshop, which is designing for the extremes with a focus on the moon, there are clear near-term needs for autonomous capabilities. And here are a few of them. I won't claim that this is comprehensive, but these are certainly ones that are important for near-term missions. And I'll talk a little bit at the end, in the next couple of slides, about some of these considerations for the Viper mission. For example, navigation is something that is clearly needed because oftentimes we talk about these systems operating without necessarily having ground control in the loop, various efficiency or limitations to things like communications. And so the capability for a system to autonomously localize itself to detect and avoid hazards is very important. Secondly, the perception that's associated with just understanding the environment or the task that the system is working on is important. And that could be things like object detection and tracking. Let's say you're trying to pick up and move a piece of equipment or work with a piece of equipment. Crew and vehicle detection and tracking could be important if we have systems, especially these robotic systems, that have to operate in and around people. Decision-making clearly is something that's needed, frankly, for almost all of these systems here in terms of planning, and that could be at various levels: activity, motion, task planning, or just basic management of resources, onboard power or communication usage. And then finally, I would contend that, think about operations, which has to do with the overall control mode, the overall ConOps design of how these systems operate. When are they operating independently? Are they operating in parallel or in series? Is there coordination, cooperation, or even collaboration between all these different pieces of for example, a lunar base? And that also then goes over into areas of things like fault management and anomaly resolution. If you really care about the way that these systems deal with those things, how do you think about that from an autonomy design point of view? And one of the things to consider then is that there certainly are problematic environmental factors. I mean, the fact that we are talking about the things that were mentioned in the first panel today, have real effects on terms of the technology and in terms of the design for the systems, in terms of the way you develop the autonomous capabilities for that. So think about terrain, for example. It certainly has very strong effects on navigation design. The way that you do localization, the way that you do hazard detection and hazard avoidance, is strongly dominated by the types and frequency of the terrain hazards. Similarly, the effect on decision-making, you think about how and when you need to do planning on board or execution or diagnosis on board is clearly driven by how benign or frankly, how difficult or extreme the terrain is that you're operating on. Similarly, you can think about illumination as being an extremely challenging factor, especially in terms of its impact on sensors. We know on the moon, most of the, I wouldn't say all, but certainly a lot of the interest in the moon these days is on the polar regions. And the polar regions, of course, because of the Earth and Sun and Moon geometry, ends up having very deep shadows, very long cast shadows. And as a result of that, we have lots of challenging effects on our use of sensors, especially things like cameras. It can also have to do with things such as on the lunar surface, the regolith opposition surge effect, which ends up to artificially brighten the appearance of the lunar soil as you're looking directly down sun. And of course, there are other factors that on the moon and certainly other planetary bodies always have impacts on surface system design. Radiation and thermal clearly, not just in terms of the robustness of components to operate, but really how that impacts overall things like vehicle health management. You think about missions that have to survive over periods of darkness. The onboard capability for doing the management of the systems, whether that's power management or comm management, or even mobility controller management, obviously directly dominated by thermal effects. And of course, long-term system capabilities can degrade if the environment from radiation and thermal have impacts on the survivability of materials. So just very quickly, let me talk a little bit about—
Just a minute or two, Harry,
Yep.
So that sounds perfect.
Great. Let me just talk very briefly about the Viper mission. For those of you who may not be familiar with this, Viper is scheduled to launch at the end of 2024, not next year, which was the original plan. 100+ day mission, up to 20-kilometer drive to basically prospect for subsurface water ice. And obviously lots of unique challenges to this having to do with the environment, light, shadows, real-time mission ops, a focus on prospecting versus on specific site-focused kind of things that we've done on Mars. The rover itself has a four-wheel mobility architecture with adjustable active suspension. It's completely battery powered with solar array charging. And because of that, that leads to lots of considerations in terms of how this robot can operate or not independently of Earth. This is my last slide here, just to point out that some of the challenges that we deal with from a point of view of autonomous operations have to do with things like power. As I said, it's an electrical power rover. And so, thinking about how you deal with the thermal management for a rover that has to survive over lunar nights, granted these are short periods that we've designed in the mission, is a big challenge. The fact that we're relying on cameras as the primary environmental sensor for navigation and for remote operations, especially remote driving, leads back to these questions of what's needed to compensate for the lunar illumination environment. And so, for example, we have had to design the use of lighting, supplemental lighting, to cope with darkness and long cast shadows. And as well as other effects in terms of thinking about how do you deal with a design where you might rely on, say, direct-to-earth comm. Well, how do you manage automatically loss of signal recovery? And that could be due to obstruction or multipath effects as well. And finally, the fact that even though we know a lot about the moon, there's still a lot of questions, a lot of uncertainty associated with things like surface composition and geometric hazards in just the area that Viper's targeted. And as I remind you that these have direct impacts on things like the design of navigation in terms of localization and hazard detection, but also more fundamentally, and as Dimi was pointing out, things like mobility controls. In any case, I'll end it right there and just remind you all that autonomy is multifaceted. It really is focused on this question of how do you operate in some robust manner, independent of external control. And for future systems, I think that probably is one of the biggest challenges we face.
Awesome, thank you. I think there's a couple of questions. I think Q&A, Terry, if you can get to those as we move on. This is giving me a lot to think about. I hope it's giving everyone else stuff too. So next we have Kris Zacny from Honeybee Robotics to round out the access panel. So Kris, we can see your slides.
Yeah, can you see my slides?
Yes.
Great. So,
do you want to put them? Nope, now they're perfect.
Are we good?
Yes, thank you.
This is good. Okay. So I'm not going to talk about mobility whatsoever, but I'm going to talk about things that require mobility, and that's various types of excavation and extraction systems. And when I was putting this presentation together, I actually had to go back to some of the work that we've done almost a decade ago. And this is probably a lesson for all of us. A lot of great stuff has been done decades ago. There is no need to reinvent the wheel. Just looking at various conferences and publications, a lot of great stuff, a lot of great data has been already revealed. So let's start with excavation and digging. Over a decade ago, actually, we put together this experimental setup, which had a scoop. It was a surveyor scoop. It had a salt bin where you could put different simulants. It had a vibratory system to compact the simulant to various densities. And it also had the scoop was mounted on a so-called like a percussive or hammering system where you could change vibration and the percussion and the frequencies and energies. And all of this was mounted on a 6 degree of freedom, so you can actually determine what are the forces during excavation. The scoop would go up and down, and the bin would go from left to right. So essentially, soil was moving towards the scoop as opposed to scoop moving towards the soil. What we found is actually something very, very interesting. If you use purely static system, so there's no vibration, no percussion, the force is relatively high, but the moment you start using frequency of percussion, the force required to dig significantly drops. These data points are average, and we've seen, and this data points also for the certain density values. The difference between maximum and minimum excavation, where you're actually doing percussion, is in this case factor of 6. We've seen factor of 10, if not more. And what this means is that it's not just the size of the excavation system that you have to deploy, but also the mobility or trafficability or drawbar pull that will be required to prevent rover from slipping. Obviously, nothing's for free. The percussion is not free. It requires energy, but this energy can be zapped from sun, from solar rays, and that's something it's literally free on a moon, but mass is not. This is, if you're curious why this excavation forces drop, this particular slide shows right on top, you have from low to high increase in the density of soil, and from top to the bottom increase in the percussion. So right on top, these are the slides or pictures where you use no percussion whatsoever, and right at the bottom, the pictures where you actually use a lot of percussion. And if you know nothing about geotechnical engineering excavation, just by looking at the amount of soil that's being accumulated in front of the scoop, you realize that the effect of that percussion has is essentially collapsing the soil in front of the scoop. If you had X-ray eyes, what you will see actually is shear planes just within the soil itself are collapsing. Right on top, they do not collapse, so this entire scoop has to excavate a large amount of soil. Right at the bottom, the soil collapses, so the amount of soil that you have to push is significantly less. And that's why the excavation forces drop. We also built to test all of this work. We built a robotic arm. It's a 5-DOF robotic arm. We put the soil bin just underneath to determine concept of operations. How would we operate robotic arm with vibratory or percussive systems and reduce obviously the excavation forces. So it's not just the rover in this case. If you reduce excavation forces, you're also reducing the size of the robotic arm. And we developed a model. So this is something that would be brought into to the mobility system, and it would be essentially back and forth and trying to size the excavation scoop or excavation blade, the size of a rover. But at a high level, we can put different inputs in terms of a mobility system, excavation tool, what sort of excavation models we would be using, what sort of a task we would be using, how many batteries we have, what sort of a soil models we're using, and then we get different outputs, the force on blade, with factor of safeties and things like this, and the life cycles of the batteries. So it's super useful model to determine, to size the excavation system before you actually go to the moon. Now, what if the soil is not granular? What if the soil is actually cemented? And this is the case if the ice in the soil is cementing agent, and what you get is something like in Alaska in winter, the frozen ground. In this case, the problem is actually quite tough. And by the way, we don't know how ice is distributed or bonded into the soil on the moon, whether it's loose or whether it's ice, or whether it acts as a cementing agent. So in this case, what you see is we use exactly the same scoop. It's a surveyor size scoop. We pushed with 3 kilonewton force. It's a huge, huge force. And the hammer energy was 5 joules. So it's actually pretty strong hammer. And this is as deep as we could go, okay? As deep as, so it's probably an inch max. And the scoop blade actually bent a little bit. So that didn't work. But at the same time, we took a hammer drill and we poked this hole right next to it in a matter of seconds. So if we have icy soil on a moon that's cemented cemented together, scooping is not going to work. Sort of like a percussive drilling is going to work. So we have to use different excavation approaches. And by the way, Terry mentioned Viper, and Viper in fact will have a percussive drill, the same diameter as this drill that you see in a picture on the left-hand side. And why icy soil is hard? We perform a number of tests to measure compressive strength of material at different moisture content. So on the y-axis, you have MPa, that's your compressive strength, which determines excavation forces. Down below on the x-axis, you have a moisture content or water content. And we did tests at both cryogenic temperature 77 Kelvin and 253 Kelvin. Bottom line is, if you have something at few weight % water and it's cryogenic, you have something the strength of a brick. And obviously, we all know you can't take a shovel and dig into the brick. It just doesn't work. And switching gears, how would you capture another lesson learned about the capturing of or doing ISRU on the surface of the moon? I've seen a lot of presentations related to ISRU and capturing of volatiles, and we've done a lot of work on this as well. And I can tell you that heating of regolith is a very easy problem. The toughest problem is actually capturing of water molecules or other volatiles that are escaping or being sublimed away from regolith. Because nothing is perfectly sealed. None of your excavation system is sealed, and water molecules and other volatiles escape in all the different directions. It's essentially like blowing a balloon and popping it and hoping that you can capture these molecules. They're gonna go in all the directions, and your probability of capturing something is very, very slim. So we looked at the designs like sniffer, porcupine, auger, and finally we narrowed down on a PVEX and a planetary volatile extractor. And the reason why PVEX works, and it's shown on the left-hand side, is because it's a coring drill. It drills down and creates a core, and this core seals to some extent the icy core inside it. And when you heat up the core that's pictured right in the middle, you heat it up, you sublime the volatiles, and then volatiles go through the swivel into the cold trap. We've done a couple of tests in our vacuum chamber, and the volatiles that we captured were enough to inflate the Mylar balloon in a vacuum chamber. So even we've done a lot of tests, and even with a system that is relatively sealed, we still lost almost 50% of water that was initially inside the soil. Lesson learned. Again, it's not really about heating; it's about capturing of water. And this table shows where you see water extracted and the percent of water extracted, it's somewhere around 50%. Okay, so these molecules essentially leak out through any path that they see available. And so how we would do this kind of water extraction system, I used to work in the mines, and things break. It's not if, it's when. So my approach to mining excavation is through the numbers. I'm a believer in the redundancy for numbers. So essentially, if something breaks, throw it out and use and have another excavation system taking it over. So here we would have a mobility system couple of mobility systems, each one with a number of these excavation systems. So if one excavation system breaks, you still have couple left. And if one rover breaks, we have more rovers. And if you take all of this into account, do a conservative assumption of 2-8% water. And by the way, 2-8% water is what you get in the sand dunes in Sahara Desert. So it's not a lot. You can mine something like 60 tons of water per year with a 10 mining rovers and 6 water extraction or PVEX systems per rover. So just to end, percussive system reduces excavation forces, it reduces the size of the robotic arm, it reduces the mass of the rover and requirements on the traction system. If ice is cemented, and Viper will tell you whether it is or not, but if ice is cemented, scooping is not going to work. And in terms of ISRU, volatile sculpture, it's not about heating, it's about capturing these water molecules that are going to escape anywhere they find easy path. So with this, happy to answer some questions.
Awesome. Thank you for that, Kris. We've got a couple in the Q&A, and I think hopefully you might be able to do those typing, but if everybody that was on the Access panel can turn their cameras back on. I know we're running a little bit long, but I'm going to take the chair's prerogative and ask a question that I hope you guys can answer. So this is for all of you, and we had folks talking about the different environments and some of the specific environment considerations that might be difficult at the lunar poles a little bit earlier, and so I was just curious if you all had thoughts, and you talked a little bit about this, most of you did, but what where do you think like the design challenges are the hardest for us in the sort of systems and types of needs you guys talked about in these different in these challenging environments? What are people going to really struggle with in the sort of near or long term?
So I think one thing that's really important to understand is that a lot of the interest these days, and this is both NASA as well as I think the commercial sector, is this idea that we can sustainably make use of the lunar surface. And that implies a lot of things for space system design that we've never had to deal with. The fact that you want to have systems that have very long duration operations, or at least like high number of duty cycles, is something that frankly is an unknown, unsolved problem right now. If you really were going to try to get to a system like Alex was talking about from the RLSO2 study, that's orders of magnitude longer and more challenging than any planetary system we've ever had to deal with, especially if they're going to involve lots of interaction through very, very extreme environments and a lot of physical interaction.
Another thing I may add is the question is, how sensitive are the architectures to the discoveries? And let me explain what that means. As we learn more, as we start fielding missions and learn more, does that change our thinking about the architecture to do things at scale? Or the architecture is robust to a broad range of discoveries related to the concentrations, to the depths at which we find these things, to the accessibility, to the distances, to the areas we need to survey. And that's something that we want to think about and explore, because if we are sensitive to the discoveries, then maybe we want to accelerate the discoveries so we can get the information we need to stabilize the architecture.
Yeah, to add to this, I think scaling is a huge issue. I think Perry touched on this, how to go from where we are today, or what has been done on the moon. Obviously, we just use, the rovers have been manned or unmanned systems have been up there to doing sustained ISRU operations is a huge deal. How do we make that leap so it can be productive? So the scaling is a huge issue. It's a huge challenge, not issue. It's a challenge. That is the challenge.
Yeah, to me, probably something that keeps me awake at night is power. The pace of space exploration is driven by available power, and a lot of folks worrying about being cold, and I can probably tell you that cold is probably the least of the problems. There are ways to deal with this, but things get hot, and things get hot very, very quickly. And ditching so much power, especially when we have a big system, big motors, big ISRU systems, that's going to be really tough. There is a program called Hot Tech that's developing technology for Venus. I think lunar exploration in the PSRs might be a customer for a lot of the high temperature technologies that's coming out for Venus applications, and that's to deal with the heat and not having to have huge radiators and dump all of this to space.
If I may add one more thing to what Kris said. So I think sometimes what's really underappreciated is how much power and thermal drive the design of the mobility and the sampling and all the strategy. And when we start thinking of the problem from the mobility at the starting point, as usually you end up with a solution that may not close on the other domains. And I think I found it sometimes more productive to understand the energetics and the thermals, which consume a lot of energy, and then work the other pieces, because there's sometimes more flexibility on the mobility side than there's flexibilities on the thermal and power.
I think that's a really good point. Terry, I'm not sure you quite agreed there. You kind of.
No, I mean, I think that all these factors, which I think Issa did a really good job in his presentation, just pointing out all these things from a robotic system design point of view, come together. And clearly, power is a big consideration, but mass has also been a dominant factor, just because of how that impacts our ability to actually launch and land different things. I love the RLSO2 study. How you could actually make that come to pass with the mass that's involved, I have no idea.
Yeah.
Also, I don't know if we have another minute, also from a robotic system perspective, and Terry touched on this in his presentation, how to get to reliable autonomy this is more from a technology push, right? Reliable autonomy for the types of operations we're talking about on the lunar surface is a very big challenge as well. It's not just about 500-meter traverse, say, just put a rover on the moon to just travel for 500 meters or such. We're talking about ISRU, the complexity, it's multiple orders of magnitude higher than anything than what we have done. And that goes through every single facet of the system, from the mechanisms, the perception, the controls, the manipulation, the operations. Terry touched on this as well, right? Because there may be multiple systems that fit within some architecture, but it's a very, very big challenge. Of course, considering the environmental conditions on the moon as well. This goes without saying. This is kind of thing everybody recognizes, that the thermal cycles, the dust, etc.
Okay. I've got one more question, kind of off of that, and then Jamie will probably pull me off the stage. So with this sort of idea of scale, if we're trying to get to, say, the RLSO2 architecture, something similar, like, full-scale production of ISRU, what do you all think is sort of like the immediate needs? We have Viper going in 24. Both Terry and Kris, you talked about some of the things that Viper is going to teach us. But what else do we absolutely need to be doing? This will come up in the breakout sessions, but I'm interested to hear what you all have to say on that too, to sort of take the steps we need to get there.
Yeah, although I work on Viper, one of the things that I like to point out to people is that, ISRU on the moon and focused on volatiles is not the only reason to go to the moon. And if you think about other reasons to better understand, especially a lot of the lunar science that might demand, say, long range, long duration surface systems, that drives other considerations. If you look at the most recent planetary decadal, the highest priority lunar surface mission is the Endurance A concept, which is basically sampling from South Polacan Basin and sampling over like 1,000 kilometers of traverse. Designing for a mission like that is radically different than designing for an ISRU focused base or even just an ISRU focused thing in a relatively small, spatial extent. So it's important to not lose sight of the fact that the moon is an interesting place for lots of reasons, and it's not just volatiles and it's not just ISRU.
Yeah, also at the high level, I think, and I don't have, of course, maybe Terry and Issa and speak to that, but I think there is, in my mind, there is a clear need to have the same way that SMD has a number of science missions, STMD must invest on technology demonstrations and technology in a very sustained and significant manner over the next decades, right? Because it's promote, obviously science drives, that's what NASA, I mean, fundamental, the mission is for science, and it may be also commercial, the commercial sector will step up on these technology demonstrations as well as we move forward. But clearly, in order to, in my mind, in order to, realize the vision of an architecture like our LOS 2, right? There has to be a number of technology demonstrations to get there. It just cannot happen in, obviously everybody understands this, right? It cannot happen in one shot. This is 10, 15 years and probably dozens, if not hundreds of demonstrations. It goes without, I mean, it's very, very clear. But I think STMD, if we can, a recommendation can come up. I think there may be some missions that are formulated for STMD, but I'm not certain about it. But I think that's essential.
I want to maybe segue into, if you think about what has been done in the decades, in terms of, advancements, computational advancement and so on, software has been just amazing, unbelievable. But other things like material science, fundamental materials, there has been, huge leaps. And when you look at the exploration and what breaks or what limits robots is essentially a simple thing. Your gearboxes break, lubrication is required and it's wearing out. So I think what will help longer stay on the moon and so on is increase fundamental understanding of the material science and lubrications and things that essentially things that break and the things that stop all the machines from working.
One thing I may add, I think when I think of exploring and scouting an area and understanding it, and I think of an infrastructure, sustained infrastructure for production and maintenance, I think there's a lot between those two, and to start thinking of what are the incremental steps. So we need to have a number of assets exploring their region, understanding their region well enough to start building thinking of the foundations of the infrastructure, the sustainable infrastructure. But there's a lot of, as we learn more, as we evolve our architectural thinking, how are we gonna eventually get to that endpoint? And is this something that's gonna come in a modular fashion where we are gonna have to, we cannot put these things there as they are, and we have to put them in pieces and we have to assemble them. That's different than assembling ISS in a clean environment. This is on the lunar surface with a lot of challenges. How would that play out? And what are the things that we need to learn how to do in terms of robotic operations or maybe robotic astronaut operations to allow us to start thinking of scaling? So there's a lot of steps between the early explorer type rovers like Viper and the infrastructure. And I think it'd be good to think about this intermediate steps as well.
Awesome. And that's actually a really good segue, Issa, because that's some of the questions, and some of the questions that we have in the breakout room actually is hopefully we can work through some of these thoughts. So thank you very much to the four of you. Those were really interesting presentations, and we appreciate your take on these questions. We're going to shift now. We're going to have a few minutes of a break and shift over to breakout rooms. And you all should have received an email from Andrea Harmon with your assigned breakout room as preparation for the workshops. So we'll give you a few minutes to transition over to those. There will be a Zoom portion for discussions, and then we're also going to be doing sort of brainstorming via Miro. And we'll do a quick run through of those for those of you who are not familiar with Miro. And then after the breakout rooms, we're going to come back here and just have a quick wrap up. So Jamie, do you have any other?
No, I figure
comments?
let's give everybody 2 or 3 minutes to get over and get settled. We'll give you a chance to get over. We've been here for a while, so if you need to take a little bio break, we totally understand that.
Yeah. We'll see you in the rooms. Thanks, everybody.